Good morning, everybody. Welcome to episode 2 of Solar Pro Saturday. Today, we're going to talk about all the different ways that you can connect your system to your home and the different infrastructure upgrades that could be involved and how to avoid some of those. So on today's agenda, we're going to talk about the different types of home connections, the type of upgrades that each might needs, how each connection style works, and also how to minimize some of these upgrades and costs. So a little background about me. I'm a former special operations fire engineer. I've been in solar for about 3 years, started my own company, KLN Solar, about 1 year ago. I specialize in applying an engineering rather than a sales approach to the system design and presentation. And we provide residential and commercial solutions, definitely specializing in battery systems. And I've been fortunate to be top 20 or higher among the power mentors since December of 2021, hopefully continuing that streak and climbing. So into the meat of it, how does solar connect? Generally speaking, you've got two different options. You can connect to the main panel or you can connect to the electric meter directly. Main panel connections are definitely the most common. Without solar, your panel is already fed by the utility. You have a single main breaker from the utility meter, which provides energy, which goes through a bus bar, to which you have your load breakers connected, which sends the power out to each individual load. The supply breakers usually center, either top or bottom. It's the one big breaker, 200 amp, 150 amp, and so on. You always want to look at that when you're looking and evaluating a meter. When you add solar to the main panel, you add an additional breaker. It results in a panel that's fed by the utility and by the solar system. The size of that added breaker is determined by the AC rating of the system. So what do you want to look for? In order to connect to the main panel, the panel, first of all, has to be up to code. It has to be capable of handling the extra feed source. So you need to look at the main breaker size. We just talked about that supply breaker. It's right in the middle, typically top or bottom. Look for the biggest breaker in there. You want to look at the size of it. Like I said, it's typically 200, 150, 125 on some of the older houses, or new ones, sometimes even as high as 400. Also important, what is the bus bar rating? If the info card, which is usually on the door, is still legible, you can read through that and find it. Typically, they'll be about the same as the main panel, but sometimes you'll get lucky and you'll find a 175 amp bus on 150 breaker. I've seen 225s on 200 amp breakers and so on. You really are getting lucky if you find that. And you also need to see, is there room for a double pole breaker? The system is going to feed through a double pole at 220 volt connection. So you got to have room for that. And if you don't have room for that, are there smaller loads that can be combined into a single breaker to allow for more room? Now we have the 120 rule. So that's the general rule of sizing for main panel connections. In essence, the system or the panel can be fed by up to 120% of its bus bar rating. Or I should say the breakers for the feed can be up to 120% of the bus bar rating, because we're operating under the assumption that there's never going to be 100% feed or 100% of the maximum breaker rating from both solar and the grid simultaneously. To figure this out, you just basically take your bus bar rating, if you can find it, multiply it by 1.2, and that is your maximum feed. You then take your utility supply breaker, add that to your solar system supply breaker, and make sure that number is less than what you determined as your maximum feed for the panel. So what happens if you need to connect a system that exceeds that 120 rule? Either you have an older 150 amp or smaller panel, you have a 200 amp panel, but you're putting a large system on it, and so on. What can you do? You're going to need an upgrade of some sort. So, and typically when you're doing any sort of permitted work on a home electrical system, when they come to do the inspection, they're going to expect that all components, even the pre-existing equipment, are going to be up to code upon completion. So you might even have to do an upgrade even if you don't exceed the 120 rule, just because the existing panel is out of code. So first and foremost, we'll start with the most expensive option. That's a main panel upgrade. If the existing main panel is insufficient in size, if it's out of code compliance, it's going to have to be replaced and upgraded. Most commonly with this, we're seeing 125 amp, 150 amp panels that we upgrade to a 200 amp. More and more lately, though, we're starting to see 200 amps that have to be upgraded to 400 amps. If you think about it, homes are having more and more high demand electrical appliances. They're shifting away from gas for things like heaters and cooking equipment. Larger homes have multiple air conditioners. We're looking at pool heaters. And a big one now is some of these rapid EV chargers. That can really put quite a load on your system. So sometimes some of these new homes even need 400 amps of feed. If your existing panel is up to compliance, but you exceed that 120 rule, one cheaper option that you can sometimes do is called a derate. With that, the panel itself is not being replaced, but we're replacing the 200 amp supply breaker down to usually 150 amp breaker. That'll be determined based on how much space you need. So for example, if you had a 200 amp bus bar and you dropped it to 150 amp breaker, you now have 90 amps available for your connection. Where if you had that same 200 amp bus bar and you kept the 200 amp panel on it, you would only have 40 amps available. And you can see the math here. You take your 200, the bus bar rating, you multiply that by 1.2 for 120%, and your maximum rating is 240. If we kept the 200 amp breaker, you subtract 240, and that's where you get your 40 amp maximum connection. You drop that breaker to 150, now you can see we have 90 amps as maximum connection. That's a much larger system that you can connect. Of course, there are drawbacks. A derate is by definition decreasing the capability of the main panel. During the day, during ideal conditions, there's not going to be a problem because the solar and the utility are supplying the same energy as the 200 amp utility fed without solar. Problem is at night, your solar is not producing, or during inclement weather, your solar is not producing much. And now you're limited to 150 amps coming in from the grid. That could have some issues if you've got high intensity night draws or high intensity draws during inclement weather, such as EV charging. Just for an example, the F-150 Lightning, the Pro charger that comes with the extended range version of that, runs at 80 amps itself, runs off a 100 amp breaker. If you have a 150 amp panel, that's only leaving you 70 amps for everything else. And if that everything includes multiple air conditioners, a pool heater, things like that, now we've got some issues. So another way to approach this is just to avoid the main panel altogether. Rather than connecting into the main panel, some jurisdictions and utilities allow line-side taps. What a line-side tap is a connection to the meter itself or between the meter and the main panel. Either way, it is on the line side or the utility supplied of the supply breaker rather than on the load side, which would be your main panel upgrade or your main panel connection, I'm sorry. So important to note, not all utilities or jurisdictions allow this connection. Fortunately, here in Florida, I use this on almost every single system that we have with the major public utilities, but a lot of our co-ops and city utilities do not allow it. So with a line-side tap, it's more cost-effective than upgrading an undersized panel. And that panel is still receiving its full amount of energy regardless, because you're not decreasing its main breaker. So if you had a 150 amp panel, it's still going to receive 150 amps, whether that energy is coming from solar or from the utility. It can still handle its full rating. It is important that this panel has to be up to code because even though we're not touching it, we are messing with the electrical system. And unlike a derate, this does not decrease your panel capability whatsoever. You have a 200 amp panel, it's still receiving 200 amps. We're not dropping it to 150 like we would with the derate. It's getting 200 amps from a combination of the solar and the utility based on what it's drawing when it's drawing it. So if you're in an area that allows line side taps, that's awesome. And I highly recommend you keep using them. That's, as I mentioned, what I do for most of my systems. If that's you, the rest of this is unnecessary and non-applicable for you. But if you are unfortunate and are operating in a region or utility that does not allow line side tap, especially if it's a region with older homes, tend to have smaller main panels, and are simultaneously need to accommodate increased usage, such as new EV charging, people who are swapping out gas for electric appliances, the following are some tips that can help you avoid costly main panel upgrades. And yes, I'm looking directly at you, California. So important to know, the AC rating or your inverter output of the system determines the breaker size, not the DC rating of the system. So when you select your inverters, you should select the inverter based on the maximum realistic real-time output, given that panel's orientation, tilt, and shade, or given the array's orientation, tilt, and shade, rather than the nameplate rating. For example, we know a 400 watt panel is not ever really producing 400 watts. If that is north facing and shaded at 20%, it's not producing anywhere close to 400 watts. So factor in things like that. Another option is you can use central inverters that allow DC oversizing. Each panel can still produce at its individual max without any clipping, and the inverter only needs to account for the real-time total output. If you have some east-west arrays, this can be especially helpful because you're really only sizing based on the total output, which we know is going to be high on the east side in the morning, high on the west side in the afternoon, but they don't overlap very much. So you don't need to max out both sides at the same time. You're just accounting for the total. So with microinverters, how should you size that? We'll have complete videos coming out in more depth on sizing for micros and string inverters. But in a nutshell, the system AC rating is the sum of the maximum AC output of each microinverter, regardless of its orientation. So with Enphase, for example, we'll think about 400 or 415 watt panels, which we're commonly working with here. You'd want an IQ8M or an 8 as your inverter size, all things being equal. That is the most appropriate selection for these panels. But when you're using those, your AC rating can climb quickly, very quickly. So if you're in an area that does not allow line side taps, it might be more beneficial for you to use the 8+, unless it's a predominantly unshaded south-facing array, in which case your clipping is going to be astronomical. It's a trade-off here that you need to find the right balance between how much energy are you clipping and losing versus the expense of the main panel upgrade. If you have north-facing arrays, if you have east-west arrays that have some shading on them, things like that, now you're not going to be exceeding that microinverter maximum output as frequently. Your clipping is more minimal. Vice versa, if you have a ground mount, for example, with no shading, your perfect array, and you have a 415 watt panel and you put an IQ8+ on there, in my opinion, you are doing malpractice. You are doing a huge disservice to your customer. Now, what about central inverter sizing? One huge advantage here is they often mitigate the trade-off between clipping and AC rating, especially if we're talking about that east-west split rather than a predominantly south-facing roof. So with the central inverters, your inverter must be sized for the total real-time production rather than the individual panel size. For example, if you have a 10 kilowatt system and it's split a perfect 50-50 east-west arrays, no shading, nothing else that we're factoring in here, you're not producing 10 kilowatts in real time, because in the morning, your east side is producing. You get some overlap around noon, but neither of them are at their peak because the sun's not perpendicular to any of those arrays. And then in the afternoon, your west side arrays are producing at their peak. So all you need to do is pick, in this case, a SolarEdge inverter that is going to accommodate for your real-time maximum output of one side or the other, or when it's overlapping the middle, but not the real-time output of the whole thing. And the peak here is, or the benefit here is, you're not clipping, you're not losing energy from those times that one side is at peak by decreasing your size, by decreasing your inverter size, because you're still able to produce on each panel at its maximum. They're able to compensate for each other a little better. Advantage here is you can end up with a smaller inverter that processes the same or higher production without any clipping, resulting in a smaller AC rating. Smaller AC rating means a smaller breaker. Smaller breaker means you're less likely to need upgrades. Final thing that we can talk about here is adding a DC coupled battery to your inverter. This can allow for even greater oversizing without any energy loss. This is important in some jurisdictions that have hard limits on AC ratings, have different net metering arrangements over AC ratings. We just encountered that in Colorado a little while ago. Or they might even have hard export limits due to some infrastructure limitations, transformer limitations in their area. So when you add a DC coupled battery, it allows a smaller inverter that meets those rules to be selected, because the excess energy that is produced by your solar panels themselves, that is in excess of the inverter rating, simply bypasses the inverter. It goes through it, goes right into the batteries, is stored and used later when needed. The added benefit here is you now have battery backup as well. Drawback, of course, batteries are expensive. So any questions? I know that was quick, pretty in-depth. Any questions, feel free to reach out. Any suggestions for future topics? Our goal here is to cover any equipment, design, engineering type questions that people feel are not being adequately covered, or if you're concerned that a lot of the training material you're seeing is biased by one company or another. Our goal here is to kind of just get to the facts, get to the data, and break it down in a way that improves everybody. The more knowledgeable you are, the better the reputation you're going to build, and that helps all of us in this industry. So feel free to reach out. If you're interested in coming to work with us, there's my link. Come join us. Happy to have you, happy to work with you and continue the training. Otherwise, we'll see you all next time.